Alrighty, welcome back to our last day of semester one. We're going to conclude our applications of derivatives lessons today with a little bit more particle motion practice. And actually, you already know how to do all of this. So if you do want to skip this video and just try these three problems on your own and look at my solutions that are posted on Teams, they're actually at the end of this document if you scroll down to the very bottom. You totally can. However, if you want to hear my warm, soothing voice talk you through it, and there might be a couple of these that you weren't sure on, then of course you're welcome to do that too. So, without further ado, let's jump into it. I suggest that you try each of these first before listening to me, because I think your brain shuts off when you're just writing down things that I do, but either way, up to you. Here we go. First problem is certainly calculator active. It has featured on many a final exam in my class, this exact same problem, because I certainly don't have the time to make up a new one, and students do fairly poorly on it. So let's get through this and see the common mistakes students make and how you can avoid those. Ready? Let's go. We're given a velocity of the particle. Now, I will tell you that first, on a free response question, they will almost never give you the position equation. Almost never, never, never. They will always give you the velocity because the velocity is the derivative of position, and they want to make sure you can work with derivatives. If you're given the position, then most of the questions they ask are kind of silly and you can figure them out without knowing calculus. Giving you velocity, though, you really need to know calculus to get things done. Second, because this is calculator active, the very first thing I did on this question was before even reading A, B, and C, I graphed this equation. So if you jump back to your graphing calculator, you'll notice that I already have this graphed, and so you should certainly do the same thing. When you graph this, the first common mistake that I see is that students try to use t in here instead of x, because they're like, oh, it's a function of t, so we'll put t in, but you really do need to match this independent variable here. If you change this to t, you can use t all the way through, but I find x makes it easier. This is in f1 of x, 84 could be in y1, whatever sounds good to you. So now, let's get to it. Find all values of t in the interval 2 to 4 for which the speed of the particle is 2. Well, we might also notice that the whole interval we're looking at is from 0 to 5, so let's take a quick second and just change our interval from 0 to 5. Menu, and although it says 0 to 5, I usually like to go one more than that in each direction, just so we don't miss anything that happens at 0 or at 5. So I'm going to go from -1 over to 6, and then take a look, and yeah, that looks pretty good. And we can pretty clearly see 0 to, I can't really see 5, so let's change our scaling really quickly. Let's have this scale by 1s. There we go. Now we can pretty clearly see this. We're going from 0 over to 5. Not bad. We can't see the bottom of this graph, and that could possibly be an issue. The top looks good, so let's change the bottom as well. And I don't know, instead of -6, let's try a comfortable -20. That's pretty good. It's going down forever. It certainly doesn't loop back up, so I think we're fine there. All right, let's get to it. Find all values between 2 and 4 for time for which the speed of the particle is 2. Two ways to set this up. Option 1 is you can take the velocity and you can solve the velocity equal to 2 or solve the velocity equal to -2. But I'll tell you right now, if you set this guy equal to 2 and that guy equal to -2, you are not solving that equation by hand. It is crazy difficult. I don't know if I can do it. If you guys figure it out, good for you. But I would not suggest it. So instead, we can solve by graphing. Now you have two ways to do it. You can graph v of t. Oh wait, we already did that. That's exciting. And then graph the equation 2 and see where they intersect. And then you can graph v of t, which we already have, and graph the equation -2 and see where they intersect. And that's fine. Alternatively, we learned last class that you could just graph the absolute value of velocity and see where that's just equal to +2. And that's what I'm going to do. I think it's a little bit more efficient. So I'm going to go up here. I'm going to quickly turn this guy off and then go down to f2 of x, absolute value of f1 of x. f1 of x. There we go. Everything's above the x-axis. We also need to graph the function 2, and it looks like they intersect. They said between 2 and 4, didn't they? 2 and 4. So it looks like they intersect in 2 spots over here. gonna move, nope, that's not what I wanted to do. Is there an undo up here? There is, excellent. So I want to move the label, please, down here. Great. All right, so we just need these two guys. If you give an extra point that's outside of the interval from 2 to 4, that's fine. You still get full points. They'll just ignore that. But we're going to analyze this graph. I am struggling. Menu, analyze graph, intersection. We'll do the first one first. Okay, and then we definitely want to make sure that we hit the plus button on that. Get a few more decimals out there. So there is our first guy. If you wonder how I'm moving it around, I'm using a mouse. You can still move the label around. This hand turns open when you go over it. And then if you click and hold the center button, notice how there's a closed hand over there. If you click and hold that, you'll be able to move your labels around the same way I am. So if you're curious, that's what's happening. Okay, then we need to find the other intersection point. Menu, analyze graph, intersection. Here to here. We also need a few more decimals. And then we're set. 3.1276 and 3.473. I will remember maybe one of those. So the only setup we need is this, and then my time values. T equals 3 point something and 3 point something else. Did really well there. Hopefully they're still saved. 3.1276, 127. You can either truncate or round. And 3.473. Great. And that's it. Nothing too bad. Part B. Find all times t in the interval where the particle changes direction, and then please justify your answers. Okay. Well, usually when we talk about change of direction, we need to look at the equation velocity, which we already have, very exciting, and we need to determine when is velocity equal to 0. But we've already graphed velocity, so let's just figure out where the graph of velocity is 0, which is a fancy way to say find the zeros of the graph of velocity. So we're going to tab up here. I'm going to get rid of this. I think we're done with that. And I'm going to get rid of this guy. I think we're done with that. And we're going to turn velocity back on. Hey there, friend. And we're going to find the zeros. I see 2 zeros here. Nothing too bad. So menu, analyze graph, 0. 1, 2. A few more decimals. We always want to go more than 3 just to make sure there's no weird rounding going on. And there we have it. 0.536 and 3.317. I want to make sure I actually got those right, otherwise your comments will roast me on that, but that looks pretty good. Now, we are not done, because although those are the right answers, we need to convince ourselves that those are the right answers. What we found is we found the places where the particle stops. So I am going to build a very quick sign chart here. It doesn't have to be perfect. We're looking from 0 to 5. We have 2 critical points. And I wanted to show you why, if you weren't, I don't know, were overly enthusiastic and said, oh, I found the answers, why those could maybe not be the answers. And for example, if we looked at our sign chart and it was positive all the way through, then we're moving right, we stop, we're moving right, we stop, and then we're moving right. The particle never changes direction there. So we do need to make sure that the signs of v of t switch or change here. And although you could evaluate different values into v of t, the faster way is just to look at the graph, I think. So if we look at the graph, to the left of our first 0, v of t is negative. In between the 2 zeros, v of t is positive. And at the end, v of t is negative. So negative, positive, negative, easy enough. And so we see we're moving left, then we move right, then we move left. Justify your answers, easy enough. V of t changes direction at t equals our 2 values, because v of t, oops, I said v of t changes direction, that's silly. The particle changes direction, blah, 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 because v of t changes sign at, and I'm just going to do some air quotes here. Should probably rewrite those if it's a real AP exam, but you get the idea. Nothing terrible. Last problem. Is the speed of the particle increasing or decreasing at a time of 4? This one's important to go through because it's something we covered at the very end of last class, and we didn't actually do any examples of this. So we should probably determine how we know if speed is increasing or decreasing, and it's a twofold process. First, we need to determine which direction the particle is moving in at 4. So the first thing I want to determine is what is v of 4? And again, calculator active. My equation for velocity is in f1 of x. So I'm going to go back to my other screen. I'm going to type in f1 of 4. And f1 of 4 gives me an exact answer. Excuse me, I would like a decimal. Negative 11.475. All right, so what does this tell us? Well, it tells us that at a time of 4, the particle is moving to the left at a velocity of 11.475. But there's one other thing we need, and the other thing we need to know is, yeah, we're moving left, but which way are we accelerating? Because if we're moving left but accelerating to the right, then we're slowing down. But if we're moving left and accelerating to the left, then you are speeding up. And so we need to find v prime of 4, which is a of 4. And to do that, well, our calculator will do all of this for us too. How exciting. So we need to go to our menu, calculus, derivative at a point. Variable is x, that's fine. We're trying to find the value of the acceleration at 4. Okay. And ddx of what? ddx of f1 of x. And we find another exact value. Whoops-a-daisies. There it is. Negative 22.295. There we have it. Because we are moving to the left and accelerating to the left, our particle's speed is increasing. So how do we write this? We say the speed is increasing at t equals 4 because v of 4 and a of 4 have the same sign. We learned at the end of last classes that when velocity and acceleration have the same sign, either they are both negative or both positive, that is when the particle's speed is increasing. There's our first one done. The last two do not have a calculator, so you can put that away if you'd like. In fact, you shouldn't have it out because you need to be able to do this without a calculator, and let's see what we're doing. Particle moves along the x-axis with velocity given by a velocity equation, very similar to the last problem. Find the acceleration of the particle. All right, well, acceleration, we know that's the derivative of velocity. I always explain how we're coming up with that acceleration equation by saying v prime of t is equal to the acceleration at t, and now we have a derivative. Nothing terrible. Negative 1 is 0. E to any power is itself, but then times the derivative of the power, and the derivative of 1 minus t is 0 minus 1. Cleaning this up a little bit, maybe we can see it's negative 1 e to the 1 minus t. Cool. Acceleration at 3. A of 3 equals negative 1 e to the 1 minus 3. Negative 1 e to the negative second, and that's fine. You can stop there. If it makes you happier, you can write it as negative 1 over e squared. All of those are equal, and so you have found the acceleration at 3, some negative number. Is the speed of the particle increasing at the time of 3? Well, same thing. We just did a problem very similar to this. First, we need to find v of 3, and we have our formula for velocity, negative 1 plus e to the 1 minus 3, negative 1 plus e to the negative second. And you might struggle a bit on this one here because eventually we need to know the sign of velocity at 3. So can you guarantee to yourself if this is positive or negative? Well, a couple ways to do that. You might say that this is negative 1 over 1 plus 1 over e squared. I'm going to need a new line here. Giving them common denominators, negative e squared over e squared, right, multiplying by e squared plus 1 over e squared gives us negative e squared plus 1 divided by e squared. Does that help? Well, I hope it does, because remember that e squared is 2.718 squared. So 2 squared is 4, 3 squared is 9, which means this is somewhere in between 4 and 9. So this is somewhere in between -4 and -9. -4 or -9 plus 1 is very much negative. So this gives us a negative answer on the top of the fraction, and e to a power is certainly positive, and a negative divided by a positive is definitely less than 0. So we can certainly conclude that v of 3 is less than 0. What about a of 3? Oh, we already found that. How exciting. A of 3 is also less than 0. So v of 3 is less than 0, and a of 3 is less than 0. So the particle's speed is increasing. And that's it. Cool. All right, part C. Find all values of t at which the particle changes direction. Well, what controls the change of direction? What controls direction? That's velocity. So we need to start by setting velocity equal to 0. That was -1 plus e to the 1 minus t equal to 0. Now we get some algebra in here. So we add our 1 to each side. And then we have to remember how to undo e so we can get at that power of t, and that is, of course, where natural log comes into play. You need to do the natural log of each side. 1 minus t, natural log of 1, any log of 1. We need to know this. Any log of 1 is 0. Add t to both sides, and we get a time of 1. So it seems to me there is only one value that causes this derivative, or this velocity, to equal 0. All right. We have to figure out if the particle actually changes direction there. So quick sign chart. You'll notice, I think, in this problem they said t is greater than or equal to 0. So technically this sign chart's from 0 to infinity. However, this function over here is good for any value. You can replace t with negative numbers. So it might actually help you to look at this sign chart from -infinity to infinity, and then realize that if we get any value of t that's negative, we can exclude it. But there's only one critical point, and that's at 1. That causes the velocity to become 0. And then we need to evaluate different numbers in our velocity. Well, we already found the velocity at 3, didn't we? We pretty much proved to ourselves the velocity of 3 is negative. So we know at 3, the particle is moving left. What about between -infinity and 1? I think 0 jumps out. It's pretty easy, right? If we did v of 0, be -1 plus e to the 1 minus 0. So v of 0 is -1 plus e. E is 2 point something. -1 plus 2 point something, definitely greater than 0. And so this is positive. Does our particle then change direction at 1? It does, because v of t changes from positive to negative. So the particle changes direction at t equals 1 because v of t changes signs at t equals 1. Some people say, well, wait, can we say v of t changes from positive to negative? Sure, that's probably even better than my answer. There's nothing wrong with that. I try to play it safe in case you switched up those. You might still get credit for it. But yeah, changes direction because v of t changes signs, because v of t changes from positive to negative is always good to go. All right, last page. Hey, we're away from equations. Now we have a graph. Let's see what this graph is telling us. A car is traveling on a straight road. And you might say, well, this road doesn't look straight. It looks like the car goes up and then stays flat and then goes down. But these are the velocities of the car. So these are positive velocities going up, which means the car is going faster and faster and faster. And then the car levels out at 20 meters per second. And then the car starts going slower and slower and slower until we get down here. And this means at a time of 24, the car was moving at a velocity of 0. So that's when they stop. But ultimately what's happening is they're on a straight line, right? And at the beginning, they go faster and faster and faster, and then they level out from 4 to 16. And then they go slow down, slow down, slow down until they get to the end. So they're moving on a straight path, just at different speeds. Now what the heck do we have to do here? For each of v prime of 4 and v prime of 20, find the value or explain why it does not exist using limits. Indicate units of measure. All right, well, if we're going to find this then, we're going to go through and find v prime of 4. And v prime of 4 means the slope of this graph at 4, but looking at that, I'm already pretty darn convinced the slope at 4 does not exist. There's a sharp point there. So how do we show that? Well, it says to use limits, so let's talk about the limits of the slopes. In particular, we're going to find the limit as x approaches 4 from the, and it's not x, it's t, isn't it? The limit is t approaches 4 from the left side of v of t. And then we're going to see, is that equal to the limit as t approaches 4 from the right side of v of t? All right, well, the limit as t approaches 4, oh, not v of t, this should be v prime, I'm so sorry, because we want to see the limit of the slopes here. Let's make that look a little nicer. The limit of the slopes, because if the slopes approach the same number, then we're fine. All right, so from the left side over here, as we're approaching, well, we're just on this steep slope, which has a constant slope. It's a line. So I'm just going to count. Looks like we go up 20 and then over 4. So the left side of the line has a slope of 20 over 4. The right side, well, the right side is just a horizontal line. The right side has a slope of 0. And I'm very confident those are not equal, but we might as well reduce and get 5 equals 0. We don't want to say any false statements, though, so we do want to go back and say 5 is not equal to 0, that's not equal, and those are not equal either, right? So we do want to put those slashes through to show that they are not equal. And then, because those are not equal, then we would say something like, therefore, v prime of 4 does not exist. Easy. V prime of 20. Well, v prime of 20, and I see a lot of students mess up on this. They go, oh, 20, there's a sharp point, also does not exist, and they go through that. But that's not where 20 is. V prime of 20 means go to a t of 20, and then take a peek at the line up here. This is also on a line, so v prime of 20, because this is in the middle of a line, I know it's going to exist, it's just the slope of this line. So maybe the easiest way to do it is to realize that we are going to go down some amount. How far? Well, we started at 20, so we're going down 20, and then to the right, well, 16 to 24, I think it's a space of 8. I think it's negative 20 over 8, or dividing by 4, negative 5 halves. It does also ask us to indicate units of measure. So just remember, in terms of rise over run, our rise here was along the y-axis, which is meters per second, and the run is along the x-axis, which is seconds. So I think v prime of 20 can be given as negative 5 halves meters per second. If you wanted to interpret it, what it means is every 2 seconds, your velocity decreases by 5 meters per second. All right, second problem. Let a of t be the car's acceleration in meters per second. For 0 to 24, write a piecewise defined function for a of t. Well, piecewise function, hopefully we've seen before, looks something like this. But the question becomes, how many pieces, and then what are the pieces? Well, the pieces, because a of t is v prime of t, and I'm going to put that over there to show the connection. V prime of t, it means the slope of v. And looking at the slope of v, I think there's only 3 slopes, aren't there? And we actually know all of them. This is a nice, clever problem here. We know that this first line has a slope of 5. We found that earlier. And it has a slope of 5 for what time values? Well, it looks like just from 0 to 4. And we want to make sure to not include the 4, because at 4 there is no slope. We showed that earlier. What's the next slope? Well, I think if we look between 4 and 16, our line is flat, so there is a slope of, or acceleration of 0, and that is from 4 to 16. And last but not least, we have our final line, which slopes downwards this way, and we found that that has a slope of negative 5 halves, and that goes from 16 to 24. And that's it. Easy peasy. Last problem. Find the average rate of change of v over the interval 8 to 20. Does the mean value theorem guarantee such that f prime, that is basically the definition of the mean value theorem, why or why not? So let's take it one sentence at a time. Find the average rate of change of v over this interval. Now this can be tricky. We know that the formula for average rate of change is that f of b minus f of a divided by b minus a. So we're really just going to use these two endpoints and find f of 20 minus f of 8 divided by 20 minus 8. But the issue with this is, what equation do we use? Do we use v or do we use v prime? But I think the trick here then is how we actually interpret the question. We have the average rate of change of v. Let's break it down. Rate of change, slope. So this to me says the average slope of v. But wait, slope of v? The slope of v, isn't that just a of t? So really what they're looking for here then is the average acceleration. And to find average acceleration, we strangely use the velocity equation. And hopefully I can convince you of that using some units right now. So what we're going to need to do is we're going to need to find v of 20 minus v of 8 divided by 20 minus 8. Okay, most of these aren't too bad. 20 minus 8, clearly 12. V of 8, well, if I look over here, v of 8 is 20, isn't it? I mean, that's on our graph. But the issue is, what is v of 20? Because over here, clearing this up a little bit, v of 20 is this point. Where is that point? Is it approximately 10, approximately 5? No, it's an exact number. And actually, we can find that exact number. How? Let's write the equation of this line and then evaluate the line at 20. So to write the equation of this line, I'll call this line y over here. We need a slope. Oh, we found the slope. The slope was negative 5/2. We also need a point at which to write this. Oh, they gave us a point, 16 comma 20. So x minus 16 plus 20. Cool. And then I want to know what is an input of 20 generate as an output. So let's find y of 20. Negative 5/2, 20 minus 16 plus 20, negative 5/2 of 4 plus 20. Simplifying, 1 and 2. Negative 5 times 2 is negative 10 plus 20, which I think is 10. So it is exactly 10. And if you guessed 10, good for you. That's great. However, we should realize that if it was 10.1, you definitely would not have gotten that point. So be careful. It's probably worth the extra 30 seconds to write the equation. This is 10. Cleaning this up, looks like negative 10 over 12, or dividing by 2, negative 5/6. But how do we know if this is velocity or acceleration? Look at the units. Velocity is in meters per second, and your time in the denominator is in seconds. So you have an answer that's in meters per second per second. This is an acceleration. And because we found it using this average rate of change formula, this is the average acceleration. All right, so we found that essentially v prime of the average v prime, I guess, the slope of the endpoints is negative 5/6. But the second question, does the mean value theorem guarantee a value of c such that v prime of c is equal to this average rate of change? Well, isn't that what the mean value theorem says? We found the slope of the secant line, and the mean value theorem says, cool, you found the slope of the secant. There is going to be some other point that is equal to the slope of the secant. You're like, well, that's mean value theorem. We might as well start writing our conclusion. But as you start to write the conclusion, using that hypothesis, we'd say something like, as v of t is continuous, and then we're like, wait, is v of t continuous? I forgot the graph. Yeah, you never have to pick up your pencil here. Definitely continuous. Love that. So as v of t is continuous on 8 to 20, and v of t is differentiable from 8 to 20, is v of t differentiable? Let's get all this junk out of the way so we can take a quick peek. From 8 to uh-oh. Isn't there a sharp point there? To me, that says that our function v of t is not differentiable. And if it's not differentiable, we can't apply the mean value theorem. And actually, you can see right away that the mean value theorem is wrong. Or not wrong, but just can't be applied, because we said we found a slope is negative 5/6. So looking at this graph, if you connect those endpoints, right, like so, that has a slope of negative 5/6. Can you find somewhere else on this interval that has a parallel slope? Well, I don't think so, because this is a slope of 0, this is a slope of negative 5/2, and this has no slope, and poof, we're out of points. There is no way we can draw a parallel tangent that has the same slope as the point that it's tangent to. And so we can definitely see that doesn't exist. And so what I'd probably do here is just cross this out. They can't read your answers if you cross them out. And we'd say the MVT cannot be applied because, not it, because v of t, be very specific, is not differentiable on 8 to 20. You might even want to be more specific, and instead of saying that, you could just say not differentiable at t equals, I think it's 16 where it's not differentiable, and that'd be fine. So hopefully today was a pretty mellow one. You got some good practice in. We talked about increasing, decreasing speeds, got some calculator use, and you're done with videos for this semester. Very exciting. The next few classes are going to be review and then a test, and then review and then the final. And I don't need to make videos for those. I'll post solutions for the things that we do in class. But that should be it. So thank you for surviving the first semester. You still have a couple tests to get through, but I have faith in you, and I'm excited to have you back on my channel next semester.